Look at any massive digital collection and you'll find an illusion. We think we're storing thousands of unique creations, but if you look closely enough and collapse the duplicates, you're often left with only a fraction of the original data. For 3D printing collectors, this illusion is an everyday reality. They manage vast, chaotic libraries of standard zip files, hoarding hundreds of gigabytes of raw, unoptimized data across external hard drives. The first layer of this bloat is completely invisible. Standard archives save the exact same geometry over and over again. If a creator includes both a supported and unsupported version of a model, standard formats simply save that entire dense mesh twice. Then comes the second layer. An army of different characters might have unique poses, but they often stand on the exact same base or hold the exact same weapon. Your computer dutifully saves those identical assets every single time they appear in a new file. Over thousands of models, these redundancies create immense, heavy files. They consume hard drive space, choke computer hardware, and make browsing a large library a painfully slow process. These massive digital libraries buckle under the weight of duplicate files, where redundant geometry creates a performance ceiling that raw storage can't solve. To solve this, Neurochrome Vault discards the standard zip format. It uses a specialized application file system designed to rethink how 3D data physically sits on the drive. It relies on an algorithm called content-defined chunking. Instead of saving a 3D model as a single massive object, the system shatters the file into distinct variable-sized pieces. Once the file is broken apart, the algorithm scans these chunks and compares them against every other piece of data in the library, hunting for identical physical geometry shared across completely different characters. When it finds a match, that duplicate geometry is recorded exactly once in a global container. Every other model that needs it simply points to that single surviving physical chunk. For slightly altered models, like pre-supported variants, the system isolates the geometry and stores only tiny delta chunks, the literal mathematical difference from the original file. By physically stripping out all of this duplicate data across thousands of files, the system can reclaim up to 60% of a user's physical hard drive space. By destroying redundancy at the geometric level, the Vault transforms bloated archives into hyperdense, lightweight data. These storage gains enable a second, critical advantage: raw performance. In an April 2026 test, engineers ran Neurochrome Vault on a severely degraded thermal-throttled mechanical hard drive. They pushed the system against a hard physical limit, a mechanical disk with a maximum sequential read speed of roughly 38 megabytes per second. This chart shows the physical reality of that hardware. At 38 megabytes per second, a standard 106 megabyte 3D model takes nearly 3 full seconds just to physically load from the disk. But watch the hyperdense data. The second progress bar races past the hardware's physical limit, fully loading and rendering that same 106 megabyte file in just 515 milliseconds. How does software read a file 5 times faster than the physical disk can actually spin? It starts with deduplication. Because the file is broken into unique chunks and compressed, the slow mechanical disk only has to read a tiny fraction of the file's nominal weight. That tiny compressed payload is aggressively pulled off the slow disk and fed directly into the computer's CPU. The multi-core processor then takes over, simultaneously handling the decryption and decompression in RAM, effectively bypassing the mechanical bottleneck of the hard drive. This architecture utilizes processing power to minimize the impact of physical hardware bottlenecks, allowing software to operate at speeds the mechanical hardware could never sustain on its own. All of this math operates in the background to provide a fluid visual experience. Because the files are packaged so efficiently, the system generates optimized low-poly meshes for zero-latency 3D previews that load in under a millisecond. Above the storage layer, the Panopticon engine scans chaotic file names from the original archives, normalizes the text, and assigns semantic tags based on the model's geometry and file paths. With the entire library organized and searchable, the Vault bridges the gap to the physical world, directly connecting to slicer software to queue models for printing. In the end, the sprawling horde of redundant files finally collapses down into a single, perfectly controlled asset. Achieving total mastery over a digital library requires the ruthless elimination of every piece of wasted data, leaving behind only the lean, high-performance geometry that truly defines the vault.